Module 3, Lesson 6, Forward Finite Divided Difference. For this module, we will be covering the concept behind numerical differentiation, different techniques involved in derivative approximations like the forward finite divided difference, the formulas that are used for evaluating your approximate derivative value, the truncated formula, and the more accurate formula, and a sample problem that will help us illustrate how this technique is applied. The derivative of your function can be graphically depicted to be the value xi substituted to your given function, thus giving you a value xi, and obtaining a line tangent to that given function fxi. The slope of this particular tangent line represents the true derivative value of your given particular function at xi. Note that under numerical integration, the derivatives that are approximated here are referred to as exact derivatives, whereby on the given function, you evaluate the derivative at a specific value of x. The function to be differentiated typically appears in one of this particular form. It may either appear as a polynomial, an exponential, or a trigonometric polynomial function. Or it may appear as a complicated continuous function that is difficult or nearly impossible to differentiate directly using your classical method. Or it may be a tabulated function, where the values of x and fx are given at a number of discrete points, as is often the case with experimental or field data. One of the few practical applications of your derivative approximation is that you could easily evaluate derivatives for numbers 2 and 3. High accuracy derivative approximation formula. The forward finite divided difference developed by Newton eventually approximates a particular derivative value with respect to your given xi and evaluates a particular function one step size ahead, which is called xi plus 1. Projecting that given particular value of x to your function gives you an fxi plus 1, and then establishes a straight line that connects your fxi and fxi plus 1. This slope of this particular straight line that interconnects your function fxi and fxi plus 1 happens to be your approximate derivative value. Note, however, that the slope of this approximate derivative value is obviously not equivalent to your true derivative value. Therefore, we naturally expect that there would be some sort of error incorporated in the process. However, you would also notice on this graphical depiction that if I lower down the step size, making my xi plus 1 closer to my reference data point xi, like this, we should be able to come up with a more accurate derivative estimate if we interconnect then the two functions, thus showing us that at a lower step size, this particular technique would eventually give us a very accurate derivative approximation. The slope then from your given particular technique is derived to be fxi plus 1 minus fxi all over xi plus 1 minus xi, which is basically a divided difference. Hence, this particular concept was the one applied for the curve fitting process under Newton's interpolating polynomial. You could likewise simplify your respective truncated version of the formula by replacing your xi plus 1 minus xi with your step size h, thus giving you a first derivative truncated version of the formula to be fxi plus 1 minus fxi all over h. The more accurate first derivative version incorporates more terms of the Taylor series expansion, giving you a first derivative equivalent to now as negative fxi plus 2 plus 4 times fxi plus 1 minus 3 times fxi all over 2h. The second derivative forward finite divided difference truncated version appears as fxi plus 2 minus 2 times fxi plus 1 plus fxi all over h squared. Whereas the more accurate second derivative version again incorporates more terms of your Taylor series expansion, turns out to be negative fxi plus 3 plus 4 times fxi plus 2 minus 5 times fxi plus 1 plus 2 times fxi all over h squared. The third derivative, forward finite divided difference truncated version, appears like this, whereby you end up with fxi plus 3 minus 3 times fxi plus 2 plus 3 times fxi plus 1 minus 3 times fxi all over h cubed. And again, a more accurate version contains more terms that are included for your Taylor series in order to compensate for accuracy of error. You'd end up with negative 3 fxi plus 1 plus 4 plus 14 fxi plus 3 minus 24 fxi plus 2 plus 18 fxi plus 1 minus 5 fxi all over h cubed. Let's try to apply that onto your given particular function. Let's say we want to evaluate the derivative of this given function at an xi value of 0.5 using a step size of 0.5. Applying then the truncated first derivative formula would end up to be like this. Thus, we require xi, which happens to be given in the problem to be 0.5, and xi plus 1, which literally means xi plus 1 step size, therefore giving us a value of xi plus 1 equal to 1. Substituting now your xi to your respective function would give us this solution with a value of 0.925. Substituting your fxi plus 1 to your function gives us this solution this time with a value of 0.2. Evaluating then the first derivative of your given function using the forward finite divided difference gives us a solution like this with a first derivative value equal to negative 1.45. In order to determine whether this particular first derivative then would be accurate, let me use the classical method, although this is not required. Given the function, the first derivative of this given function would turn out to be negative 0.4x cubed minus 0.45x squared minus x minus 0.25. I then substitute your xi value of 0.5 to this first derivative, which eventually gives us a solution like this, and a first derivative actual value equal to negative 0.9125, showing that this particular derivative estimate at a step size of 0.5 obviously contains an error. If we establish then the absolute difference between this actual value against your approximate derivative value, you'd end up with an error equal to 0.5375. Thus, based from our graphical depiction, in order to have a more accurate derivative estimate, we could simply lower down this step size h. Let's apply then that same forward finite divided difference truncated formula onto our given function, this time with a step size of 0.25, which is much lower than your previous 0.5. Applying then the truncated formula requires us to evaluate xi and xi plus 1. In this case, our given xi was 0.5, and our xi plus 1 is now computed to be 0.5 plus 1 step size, which gives us a value of 0.75. Note that when we substituted xi to your given function, it gave us a value of 0.925. Substituting now xi plus 1 to your function gives us this solution with a value of 0.6363. Thus, when applying the forward finite divided difference truncated version, you'd end up with this solution with a derivative estimate value equal to negative 1.1547. If we then compare that to our previous computed actual derivative value, which is negative 0.9125, we would end up with an error now of about 0.2422, showing that yes, lowering the step size do indeed improve accuracy for our given particular derivative estimate. Note that the first derivative also contains what you call a more accurate derivative formula. Let's try to apply that using a step size of 0.25 onto our given function. This is the more accurate first derivative formula, which requires us to evaluate fxi plus 2, fxi plus 1, and fxi. Note that xi is given to be 0.5, and we already evaluated for the function fxi to be 0.925. Your xi plus 1 would mean xi plus 1 step size, giving us a value of 0.75, which we have also previously computed to be, when substituted to our function, as 0.6363. And fxi plus 2, which means xi plus 2 step sizes with a value of 1 now, when substituted to our function as we have previously solved, your fxi plus 2 would simply be equivalent to 0.2. Thus, when substituting these function values to your first derivative estimate, it gives us this solution with a first derivative more accurate value now to be negative 0.8594. and an actual derivative which was negative 0.9125, having an error this time of about 0.0531, showing us that yes, a more accurate formula do indeed give us a much closer derivative value. However, the more accurate formula obviously incorporates more terms as seen from your Taylor series expansion. Another way to improve your derivative estimate techniques is based from the Richardson's extrapolation formula, which is very similar to your Romberg integration. That is, if we then compare two derivative estimates, just like what we do to the integral value. This is the exact same formula for your Romberg integration, except all values of integrals are now replaced by derivatives. It can be shown that the error of this estimate is 0h raised to 4. Thus, when two derivative estimates of 0h squared is used to evaluate for a derivative value, then it yields a new estimate with an error of 0 raised to h raised to 4. The improved estimate for the derivative for a special case wherein the interval basically is half the previous value would simply be like this, much like the applied Romberg integration formula. Note that dH1 is the derivative estimate at a step size of h1, which is considered to be less accurate. dH2 is the derivative estimate at the step size of h2, which is considered to be more accurate since h2 has a smaller step size than your h1. And this particular condition is known as the extrapolation condition. If this particular condition is not met, then the formula won't be applied. K is also referred to as the extrapolation order on the formula with the minimum value of K equal to 2. Let's try to apply then this particular improved formula using Richardson's extrapolation on our previous function on the forward finite divided difference using the step size h equal to 0.5 and h equal to 0.25. At h equal to 0.5, take note the derivative estimate was negative 1.45. And at h equal to 0.25, which is half the previous step size, the new derivative estimate turns out to be negative 1.1547. Thus, when we apply the Richardson's extrapolation formula, we would end up with this solution and a derivative estimate now equal to negative 1.0563. Note that this particular derivative estimate turns out to be better or more accurate than the two previous derivative estimates at 0.5 and at 0.25, as seen from our actual first derivative value. This ends Module 3, Lesson 6.